Welcome to this video on trigonometric functions. In this chapter, we will explore the journey of generalization, breaking out of the confines of simple triangles. Trigonometry, from the Greek for triangle measure, has evolved significantly. From its ancient roots with mathematicians like Aryabhata to its modern role modeling everything from ocean tides to atomic states, it is a fundamental tool for understanding our universe. We now define angles as continuous rotations. An anti-clockwise rotation creates a positive angle, while a clockwise rotation generates a negative one, moving from an initial side to a terminal one. To generalize, we look beyond degrees to radians. A radian is the angle subtended at the center of a circle by an arc equal in length to the radius, providing a unit tied directly to circular geometry. This table highlights the differences between degrees and radians. While degrees are useful for navigation, radians are essential for calculus and physics, with simple formulas to convert between the two. By mapping angles onto a unit circle, we merge trigonometry with the coordinate plane. This reveals the universal engine, the Pythagorean identity, where the sum of cosine squared and sine squared always equals 1. We can expand our trigonometric family to include secondary functions like secant and cosecant. A key takeaway here is periodicity. Sine and cosine values repeat every 2 pi radians. The sign of these functions depends on the quadrant. You can remember which functions are positive using the mnemonic all sine tangent cosine, or ASTC. Tangent values can behave uniquely. Because tangent is sine divided by cosine, it becomes undefined at odd multiples of pi over 2, as the value approaches infinity at those boundaries. This matrix summarizes the behavior of our trigonometric functions, including their domains, ranges, and how they transition through different values. Trigonometric identities act as the rules for the celestial circle. We can categorize them into shifters, combiners, and multipliers, which allow us to navigate complex relationships between angles. First, the shifters. Parity identities explain how negative angles affect coordinates, while phase shifts show how rotating by 90 degrees allows us to swap sine and cosine values. Next, the core combiners. These formulas for the sums and differences of two angles show how sine and cosine functions interact with one another. Building on that, we have identities for tangent and cotangent combinations, which are derived from the primary sine and cosine formulas. Finally, we have the multipliers. By setting the two angles to be equal, we unlock the double angle formulas for sine, cosine, and tangent, completing our mathematical toolkit. Moving further, we reach the triple angle formulas. These multipliers, including sine 3x, cosine 3x, and tangent 3x, expand our ability to simplify expressions involving higher order angular inputs. The transformers allow us to convert sums or differences of trigonometric functions into products. This process is incredibly useful for rapid simplification when solving complex equations. Here is the ultimate synthesis map. It captures the metric, reciprocal linkages, combiners, and multipliers we have discussed, all centered around the fundamental Pythagorean identity. As we conclude, remember this thought from Milne: a mathematician knows how to solve a problem, he cannot solve it. Keep exploring and enjoy the beauty of trigonometry.